Imagine watching the entire history of the universe as though it were a film. Galaxies slowly gather from clouds of gas, stars ignite, burn for billions of years and collapse. Black holes merge. Entire galaxy clusters drift apart as space itself expands. Every event, from the birth of the first atom to the explosion of the most distant supernova, seems to unfold in an unbroken stream, as though reality were a perfectly smooth movie. But what if it isn't? What if the universe is hiding something so fundamental that we have never directly observed it? Not because it is too far away, not because it is too small to build a telescope for, but because every event you have ever witnessed, even the beating of your own heart, the light entering your eyes and the firing of neurons inside your brain, depends on it. Physics has already taught us that there is a smallest speed limit. Nothing outruns light in empty space. It is also hinted that there may be a smallest meaningful length, known as the Planck length, beyond which our current theories stop making reliable predictions. But there is another question, one that is asked far less often, and yet it may be even more profound. Can an event itself be divided forever? If someone claps their hands, does that action happen through an infinite sequence of ever smaller moments? Or is there, hidden beneath everything we experience, a final, indivisible unit of change, a smallest possible event beyond which reality simply cannot be broken? At first, this sounds like philosophy, but it is actually one of the deepest unanswered questions in modern physics. The answer reaches into quantum mechanics, Einstein's relativity, black holes, the earliest moments after the Big Bang, and perhaps even the true architecture of space and time themselves. If there really is a smallest possible event, then the universe may not flow continuously at all. Time itself may not be infinitely smooth. Reality could possess a hidden grain, too fine for any experiment yet performed, but fundamental to everything that exists. And if there isn't, then nature allows an infinite hierarchy of ever smaller changes, with no bottom layer waiting beneath them. The remarkable part is that physics has not settled this question. Even today, the greatest scientific theories ever created begin to disagree precisely where this mystery becomes unavoidable. To understand why, we first have to ask something surprisingly difficult. What exactly is an event? Most people think they already know the answer. A lightning strike is an event. A star exploding is an event. A person taking a single breath is an event. These seem obvious because our brains naturally divide the world into beginnings and endings. But physics defines an event much more precisely. An event is simply something that occurs at a particular place and a particular time. That definition sounds almost disappointingly simple, yet it quietly changed science forever. Before the 20th century, space and time were treated as separate things. Space was the stage. Time was the universal clock. Events merely happened within them. Then Albert Einstein overturned this picture. According to special relativity, published in 1905, there is no universal clock ticking identically for every observer in the universe. Two people moving relative to each other may disagree about how much time has passed between the same pair of events. They may even disagree whether two distant events happened simultaneously. The one thing they always agree upon is that an event itself exists. An event becomes the fundamental building block of space-time. Imagine placing tiny dots throughout the universe. Every flash of light, every collision between atoms, every photon leaving a distant star, every nuclear reaction inside the sun, every heartbeat you have ever experienced. Physics treats each of these as individual points inside a four-dimensional fabric called space-time. Instead of imagining the universe as objects moving through empty space, Einstein encouraged physicists to think of reality as an enormous network of events connected by cause and effect. The stars overhead are not merely objects. Their histories are woven from unimaginable numbers of individual events. Every second, our sun converts roughly 600 million tons of hydrogen into helium through nuclear fusion. Each fusion reaction is itself a collection of quantum events involving protons overcoming electromagnetic repulsion through quantum tunneling. Multiply that by billions upon billions of reactions every second. Then multiply again by the estimated hundreds of billions, perhaps even trillions of galaxies filling the observable universe. The scale quickly escapes ordinary imagination. Every instant across the cosmos contains more individual physical events than there are grains of sand on every beach on Earth. And yet, physics asks an astonishing question. Can each of those always be divided into smaller ones, or does nature eventually refuse? The question becomes surprisingly familiar if we borrow an analogy from cinema. When you watch a movie, the action appears perfectly smooth. A bird flies effortlessly across the sky, a person smiles naturally, water flows continuously. But pause the film. Suddenly, the illusion disappears. What seemed continuous becomes a collection of individual frames. The motion was never truly continuous inside the movie itself. Your brain stitched together thousands of still images into smooth movement. Now imagine asking whether reality works the same way. Is the universe an infinitely smooth film, or does it also possess hidden frames too tiny to notice? If such frames exist, they would not necessarily resemble digital pixels or computer graphics. Nature rarely imitates human inventions. But the analogy helps reveal the central mystery. Is continuity real, or merely an illusion emerging from something more fundamental? For centuries, mathematicians became comfortable describing nature using continuous equations. Calculus, developed independently by Isaac Newton and Gottfried Wilhelm Leibniz during the 17th century, assumes that quantities can change by arbitrarily small amounts. Velocity changes continuously. Position changes continuously. Time flows continuously. The equations work astonishingly well. They predict planetary motion with extraordinary precision. They describe ocean tides, sound waves, falling apples, and spacecraft navigating billions of kilometers through the solar system. Even today, continuous mathematics remains one of humanity's greatest intellectual achievements. Yet history has repeatedly shown that successful mathematics does not always reveal what reality truly is. Heat once appeared continuous. Later, physicists discovered atoms. Electric charge once appeared continuous. Then came the electron, revealing that charge exists only in discrete units. Light once seemed like an endlessly flowing wave. Then Max Planck proposed in 1900 that light exchanges energy in tiny packets, quanta. One after another, nature has surprised us by replacing smoothness with discreteness. That pattern naturally raises another possibility. Could time itself eventually join that list? Not because someone wants reality to resemble a computer simulation, not because science fiction suggests it, but because the mathematics describing gravity and quantum mechanics begins breaking apart when we push both theories toward the smallest imaginable scales. That breakdown is not a minor technical inconvenience. It signals that our understanding of reality becomes incomplete. Somewhere beyond our current knowledge, another description must exist. Whether that description is continuous or discrete remains one of the greatest open questions in science. Long before modern physics, surprisingly, philosophers were already wrestling with this mystery. Around the 5th century BCE, the Greek philosopher Zeno proposed a series of paradoxes designed to expose strange consequences of infinite divisibility. One of his most famous arguments imagined a runner attempting to reach a finish line. Before reaching it, the runner must first travel half the distance. Before reaching halfway, they must first travel 1/4. Before that, 1/8, then 1/16. The process continues forever. If every distance can always be divided again, then completing infinitely many steps appears impossible. Yet runners clearly do cross finish lines every day. For centuries, this paradox puzzled philosophers and mathematicians alike. Calculus eventually resolved the mathematical issue by showing that infinitely many decreasing intervals can possess a finite total. But Zeno's deeper question never disappeared. Can reality itself truly be divided without limit? Or is mathematics describing something more idealized than nature actually allows? Modern physics has transformed that ancient philosophical puzzle into an experimental scientific question. The answer, if discovered, would reshape our understanding of everything from quantum particles to the birth of the universe itself. And perhaps the first clues are hidden not inside laboratories on Earth, but among the oldest light still traveling across billions of galaxies toward us. The oldest light in the universe has been traveling for almost the entire age of cosmic history. Long before our sun existed, before Earth formed from a disk of dust, before the Milky Way had finished assembling its spiral arms, these photons had already begun their journey. At this very moment, while you are listening to these words, trillions of them are silently passing through your body every second. You cannot see them. Their wavelengths have been stretched by the expansion of space itself, until they now belong to the microwave part of the electromagnetic spectrum. Yet they carry a message from an era only about 380,000 years after the Big Bang, when the universe was still so hot that atoms could not exist. This ancient glow is known as the cosmic microwave background, first accidentally discovered in 1965 by Arno Penzias and William Wilson. They were not searching for the beginning of the universe. They were trying to eliminate persistent radio noise from a large horn antenna at Bell Laboratories. They checked the electronics, corrected possible interference, and even removed pigeons nesting inside the antenna. But the faint signal refused to disappear. Unknown to them, they had detected the oldest light humanity has ever observed. The discovery became one of the strongest confirmations of the Big Bang model and earned them the Nobel Prize in Physics in 1978. More importantly, it gave physicists something extraordinary: a photograph of the infant universe. When satellites such as COBE, WAMAP, and later the European Space Agency's Planck spacecraft mapped this radiation with increasing precision, they found something astonishing. The early universe was almost perfectly uniform. Across billions of light years, the temperature differed only about 1 part in 100,000. That tiny difference changed everything. Those microscopic fluctuations became the seeds from which every galaxy eventually formed. Every spiral galaxy, every elliptical galaxy, every galaxy cluster, every supercluster stretching hundreds of millions of light years. Even the Milky Way itself owes its existence to fluctuations so incredibly small that if you could somehow enlarge the early universe to the size of Earth, the tallest mountains in its temperature would have been only a few meters high. Everything we see today, stars, planets, oceans, living organisms, and eventually conscious observers capable of asking questions about the universe, grew from imperfections that were almost unimaginably tiny. Already we encounter a profound lesson. Nature often hides its greatest consequences inside its smallest structures. The galaxies filling the night sky did not begin as giant objects. They began as quantum fluctuations. That statement sounds almost unbelievable. How can something governed by quantum mechanics eventually become an object containing hundreds of billions of stars? Yet, according to the inflationary model of cosmology, quantum fluctuations occurring during the first tiny fraction of a second after the Big Bang were stretched by an episode of extraordinarily rapid cosmic expansion. Those fluctuations became the density variations later observed in the cosmic microwave background and ultimately evolved into the vast cosmic web spanning the observable universe. When astronomers map millions of galaxies today using surveys such as the Sloan Digital Survey and the Dark Energy Survey, they do not find galaxies scattered randomly through space. Instead, they discover enormous filaments stretching across hundreds of millions of light years, connected like strands of an unimaginably vast three-dimensional spider web. Between these filaments lie enormous voids where comparatively few galaxies exist. The largest of these structures are so immense that light itself requires hundreds of millions of years merely to cross them. Yet remarkably, computer simulations beginning only with the tiny fluctuations measured in the cosmic microwave background reproduce this same cosmic web with astonishing accuracy. It is one of the greatest triumphs of modern cosmology. But hidden inside this success lies another mystery. Those original quantum fluctuations occurred under conditions where our current theories become dangerously incomplete. To understand why, imagine rewinding the history of the universe. The galaxies disappear first. Stars dissolve back into gas. Atoms are stripped apart into nuclei and electrons. Eventually, even atomic nuclei cannot survive. The universe becomes an expanding ocean of elementary particles moving at nearly the speed of light. Continue rewinding. Temperatures climb into trillions of degrees. Matter and radiation become almost indistinguishable. The four fundamental forces of nature begin behaving differently from how they do today. Then continue further. 1 second after the Big Bang, 1 millisecond, 1 microsecond, 1 billionth of a second. Each step backward carries us into conditions impossible to recreate completely inside any laboratory on Earth. Yet physics continues functioning remarkably well. Our equations still describe nuclear reactions, particle interactions, neutrinos streaming through space, and the synthesis of the light elements that still fill the cosmos today. But then something remarkable happens, not gradually, almost suddenly. Around 10 to the minus 44th seconds after the Big Bang, 1/10 million trillion trillion trillionth trillionth of a second, our best theories simply stop agreeing with each other. It is as though the mathematical language describing reality begins to lose its grammar. This moment is known as the Planck time. It is not merely an extremely small number. It represents the boundary where two magnificent pillars of modern physics collide. On one side stands Einstein's general theory of relativity, published in 1915. It describes gravity not as a force pulling objects together, but as the curvature of space-time itself. Massive objects tell space-time how to curve, and curved space-time tells matter how to move. This theory predicts the bending of starlight around the sun, the expansion of the universe, gravitational waves detected by LIGO in 2015, the existence of black holes, and even the precise operation of GPS satellites. Every experimental test for more than a century has confirmed its predictions with extraordinary precision. On the other side stands quantum mechanics, developed through the work of Max Planck, Niels Bohr, Werner Schrödinger, Paul Dirac, Wolfgang Pauli, Richard Feynman, and many others. Quantum theory governs atoms, electrons, photons, and every elementary particle ever observed. It predicts atomic spectra, semiconductors, lasers, superconductors, nuclear decay, and the behavior of matter with astonishing accuracy. In fact, some predictions of quantum electrodynamics agree with experiments to more than 10 decimal places, making it the most precisely tested scientific theory ever constructed. Separately, these theories are masterpieces. Together, they refuse to cooperate. Gravity assumes spacetime is smooth and continuous. Quantum mechanics insists that uncertainty is woven into the fabric of nature. When physicists attempt to quantize gravity using the same methods that successfully describe the other forces, the mathematics explodes into infinities that cannot be removed consistently. It is not because physicists lack cleverness. Generations of the brightest minds have spent decades attacking this problem. The difficulty appears to lie deeper in our assumptions about reality itself. John Archibald Wheeler, one of the 20th century's greatest theoretical physicists and the scientist who coined the term black hole, once suggested that spacetime near the Planck scale may resemble what he called quantum foam. Instead of being perfectly smooth like a calm lake, spacetime at unimaginably tiny distances might boil with violent fluctuations. Tiny wormholes could appear and disappear. Geometry itself might fluctuate. Even the concepts of before and after could lose their ordinary meaning. If Wheeler was even partially correct, then asking what happened before the Planck time may be as meaningless as asking what lies north of the North Pole. The very stage on which events occur may not yet have existed in any recognizable form. This is where our question becomes even more fascinating. If spacetime itself ceases to behave continuously below the Planck scale, then what exactly is an event? Can an event still be divided into smaller and smaller pieces? Or does nature finally reach a point where the question itself no longer makes physical sense? Modern physics does not yet know. And that uncertainty is not a weakness. It is one of the clearest signs that humanity has reached the frontier of knowledge, where every new idea has the potential to transform our understanding of reality itself. One of the most remarkable aspects of physics is that the Planck scale was not discovered by looking through a telescope or by smashing particles together inside a laboratory. It emerged from pure reasoning. Long before anyone could imagine building machines powerful enough to probe the earliest moments of the universe, physicists realized that three constants of nature seem to define an entirely new regime of reality. Those constants are deceptively familiar. The first is the speed of light, c. It does much more than determine how fast light travels. In Einstein's relativity, it is woven into the geometry of spacetime itself. Every observer, regardless of their motion, measures exactly the same value. It acts as the ultimate conversion factor between space and time, allowing distance to be measured in units of time and vice versa. In a profound sense, it is not merely the speed of light, it is the speed at which cause and effect propagate through the universe. The second is g, Newton's gravitational constant. Unlike the speed of light, gravity is astonishingly weak. A small refrigerator magnet effortlessly overcomes the gravitational pull of the entire Earth on a paperclip. Yet gravity dominates the architecture of the cosmos because it is always attractive and acts over infinite distances. It shapes stars, galaxies, galaxy clusters, gravitational lenses, and the expansion history of the universe itself. The third constant is h, Planck's constant. This tiny number governs the quantum world. It determines the smallest action involved in physical processes and sets the scale at which wave-like and particle-like behavior become inseparable. Without Planck's constant, atoms would not possess stable electron orbitals. Chemistry would collapse. Molecules could never form. Neither stars nor living organisms could exist. These three constants originate from entirely different branches of physics. One belongs to relativity. One belongs to gravity. One belongs to quantum mechanics. Yet when Max Planck combined them mathematically in 1899, they produced a completely new family of natural units: a length, a time, a mass, a temperature. Not chosen by humans, not based on the Earth rotating around the sun, not based on kilograms stored inside laboratories. These units arise entirely from the laws of nature themselves. That realization alone is extraordinary. It suggests that the universe possesses its own built-in system of measurement, one that would be identical for any intelligent civilization anywhere in the cosmos. An astronomer living inside a galaxy 2 billion light-years away, orbiting an entirely different kind of star, would derive exactly the same Planck units. Nature appears to carry its own ruler, its own clock, its own scale. Among these, the Planck time is especially mysterious. Approximately 5.39 times 10 to the minus 44th seconds. Trying to imagine such a duration quickly defeats intuition. Light, traveling at its maximum possible speed, covers only one Planck length during one Planck time. That distance is about 1.6 times 10 to the minus 35 meters. To appreciate how small this really is, consider the following comparison. A proton measures roughly 10 to the minus 15 meters across. The Planck length is smaller than a proton by about 20 orders of magnitude. If a proton were enlarged until it became the size of the observable universe, a Planck length would still be smaller than a single atom. And the observable universe itself spans approximately 93 billion light-years. Numbers like these reveal something important. The Planck scale is not simply very small, it is unimaginably removed from direct human experience. Even the most powerful particle accelerator ever constructed, the Large Hadron Collider near Geneva, reaches collision energies around 10 to the 13 electron volts. The Planck energy is roughly 10 to the 28th electron volts. That is 15 orders of magnitude higher. To bridge that gap by simply building a larger accelerator would require a machine vastly beyond planetary dimensions. Depending on the accelerator technology used, it could rival the size of Earth's orbit around the Sun, or far larger. The required energy would be equally impractical with any technology we currently understand. This is why physicists cannot simply look at the Planck scale. Nature has hidden it behind an almost impossible experimental barrier. Instead, researchers search for indirect evidence: tiny deviations in gravitational waves, subtle signatures in the cosmic microwave background, possible violations of Lorentz symmetry, quantum fluctuations frozen into the earliest light, black hole evaporation, ultra-high energy cosmic rays arriving from distant galaxies. Every one of these observations becomes a possible window into physics beyond our current theories. This situation has an interesting historical parallel. No one had ever seen an atom when Ludwig Boltzmann argued that gases consist of microscopic particles constantly moving in random directions. Many respected physicists rejected the idea because atoms seemed forever beyond observation. Only decades later did Einstein's explanation of Brownian motion and Jean Perrin's experiments provide overwhelming evidence that atoms were real. Modern quantum gravity may be in a similar position. We may already possess indirect clues while lacking the technology to observe the underlying structure directly. This possibility motivates some of the most ambitious scientific projects ever undertaken. But another question emerges almost immediately. If the Planck time is so fundamental, does that automatically mean that time itself comes in discrete ticks? Surprisingly, the answer is no. This is one of the most common misconceptions in popular science. The Planck time is not currently known to be the smallest indivisible unit of time. Instead, it marks the point where our existing equations become unreliable. There is an enormous difference between these two statements. Imagine possessing a map that accurately describes every road across an entire continent. Eventually, the map reaches the coastline. Beyond that point, the paper is blank. The blank region does not prove that nothing exists beyond the coast. It simply tells us that the map no longer contains reliable information. The Planck time functions in much the same way. General relativity and quantum field theory together provide astonishingly accurate descriptions of reality over an enormous range of scales. But when gravity becomes as strong as quantum effects, the mathematical framework itself reaches the edge of its domain. Beyond that edge lies unknown territory. This distinction is essential because different approaches to quantum gravity make radically different predictions. Some theories suggest spacetime really is discrete. Others argue that spacetime remains continuous while possessing an entirely new quantum structure. Still others propose that spacetime is not fundamental at all, that it emerges from something even deeper. This last possibility is especially fascinating because it overturns one of our oldest assumptions. For thousands of years, humans have treated space and time as the stage upon which the universe performs. What if the stage is actually part of the performance? The idea sounds almost impossible at first. Yet modern theoretical physics increasingly hints that space-time itself may be an emergent phenomenon. A useful analogy comes from temperature. When you touch a warm cup of tea, the warmth feels like a fundamental property of the liquid. In reality, temperature does not exist at the level of a single molecule. An individual molecule has energy and velocity, but not temperature. Temperature emerges only when countless molecules interact statistically. For almost every scientific revolution in history, progress began when physicists discovered that something they believed to be fundamental was actually an approximation. The Earth felt stationary. It is moving. The Sun appeared to orbit the Earth. It does not. Matter looked continuous. It is atomic. Light seemed purely wave-like. It is also quantized. Again and again, reality has revealed a deeper layer beneath ordinary experience. This historical pattern naturally raises an uncomfortable possibility. Perhaps space-time itself belongs on that list. To appreciate why this idea is taken seriously, we need to examine something physicists call locality. At first glance, locality appears almost self-evident. If one event influences another, that influence must travel through the space between them. Nothing simply reaches across the universe instantaneously. Newton himself was uneasy with his own law of gravity because it appeared to involve what he called action at a distance. Somehow, the Sun influenced Earth across 150 million kilometers of empty space without anything visible connecting them. Einstein solved this puzzle by replacing gravitational force with geometry. Earth is not being pulled toward the Sun by an invisible rope. Instead, it follows the curved geometry of space-time created by the Sun's mass. Gravity is no longer something transmitted through space. It is a manifestation of space-time itself. For over a century, this picture has passed every experimental test. But quantum mechanics introduces an unexpected complication. In 1935, Albert Einstein, Boris Podolsky, and Nathan Rosen published what is now known as the EPR paper. They believed quantum mechanics was incomplete because it predicted correlations between distant particles that seemed almost impossible to reconcile with ordinary notions of locality. Imagine two particles created together in a single quantum process. They separate. One travels toward a galaxy billions of light-years away. The other remains near Earth. According to quantum mechanics, certain properties of these particles can remain entangled. Measuring one immediately determines the correlated outcome for the other, even though no usable information is sent faster than light. Einstein famously dismissed this implication as spooky action at a distance. For decades, many physicists hoped hidden variables would eventually restore a more intuitive picture of reality. Then came John Bell. In 1964, Bell proved something astonishing. He showed that no theory based simultaneously on locality and predetermined hidden variables could reproduce all the predictions of quantum mechanics. His theorem transformed a philosophical debate into an experimental one. Beginning with the pioneering experiments of John Clauser and Stuart Friedman in the 1970s, followed by Elaine Aspect's increasingly sophisticated tests in the 1980s, and later experiments by Anton Zeilinger and many others, Bell's inequalities were repeatedly violated exactly as quantum mechanics predicted. The 2022 Nobel Prize in Physics recognized these foundational discoveries. The universe appears to possess correlations that cannot be explained by any simple picture in which physical properties exist independently and interact only through local classical mechanisms. Notice something remarkable. Quantum entanglement does not allow faster-than-light communication. Einstein's speed limit remains intact. Relativity survives. Yet entanglement tells us that reality is more deeply interconnected than classical intuition ever imagined. Many modern researchers suspect this is not an isolated curiosity. It may be hinting at the microscopic architecture of space-time itself. In recent years, an extraordinary idea has gained momentum among theoretical physicists. Perhaps entanglement creates geometry. At first, this sounds almost mystical. It is anything but. The idea emerged from precise mathematical work involving black holes, quantum information theory, and string theory. Juan Maldacena's ADS-CFT correspondence, proposed in 1997, suggested an astonishing relationship between gravity in one spacetime and a quantum theory existing on its boundary. Years later, Mark van Ramstonk argued that increasing quantum entanglement naturally causes spacetime to become connected, while reducing entanglement causes spacetime to fragment. Then came another provocative proposal from Leonard Susskind and Juan Maldacena: ER equals EPR. The name itself combines two famous ideas. ER refers to Einstein-Rosen bridge, a mathematical description of a wormhole. EPR refers to quantum entanglement. The proposal suggests that entangled particles and microscopic space-time connections may represent two descriptions of the same phenomenon. This idea remains speculative. No experimental confirmation yet exists. But what makes it fascinating is not science fiction imagery of wormholes. It is the possibility that geometry itself may emerge from patterns of quantum information. If true, then distance would not be fundamental. It would be a consequence. Think about that for a moment. When you measure the distance between two galaxies, you naturally imagine that space already exists and the galaxies simply occupy different locations within it. But according to this emerging viewpoint, the network of quantum relationships may come first. Space emerges afterward. It would be one of the greatest reversals in scientific history. The consequences reach directly back to our original question. Suppose space-time is not fundamental. Suppose it emerges from a deeper quantum structure. Then asking for the smallest event in space-time resembles asking for the smallest ocean wave while ignoring the existence of water molecules. The wave is real, but it is not fundamental. The truly fundamental process occurs at another level entirely. This brings us to one of the boldest attempts to describe that hidden level: loop quantum gravity. Unlike string theory, which introduces additional dimensions and tiny vibrating strings, loop quantum gravity begins by asking whether Einstein's spacetime itself should be quantized. Carlo Rovelli, Lee Smolin, Abai Ashtekar, and several other physicists developed this approach during the late 20th century. Their starting point is surprisingly conservative. Keep Einstein's insight that gravity is geometry. Then quantize the geometry itself. In this framework, space is not infinitely divisible. Instead, quantities such as area and volume possess discrete spectra, much like the quantized energy levels inside an atom. Imagine zooming into space. At first, everything appears smooth. Planets, mountains, cells, atomic nuclei, quarks. Continue further. Eventually, according to loop quantum gravity, smooth geometry disappears. Instead of a continuous fabric, space resembles an unimaginably tiny network known as a spin network. These are not particles floating inside space, they're the microscopic structure from which space itself emerges. Each link carries quantized geometric information. Each node represents a tiny chunk of volume. Distance is no longer infinitely divisible because geometry itself comes in discrete units. The picture becomes even more interesting when time enters the story. As these spin networks evolve, they generate what physicists call spin foams. The name is beautifully descriptive. Just as bubbles appear and disappear inside ordinary foam, quantum geometries continuously rearrange themselves. A spin foam does not represent objects moving through space-time. Instead, it represents space-time itself evolving. In this picture, an event acquires an entirely new meaning. An event is no longer simply something happening. It becomes a microscopic transition between quantum geometries. The smallest possible event would correspond to the smallest allowed change in the spin network. Notice how radically different this is from our everyday intuition. We usually imagine time as a river carrying events forward. Loop quantum gravity suggests that what we call time may emerge from countless elementary transitions occurring in an underlying quantum geometry. Even more surprising, many of the fundamental equations of the theory do not contain time in the familiar sense at all. This echoes a profound observation made by physicist Bryce DeWitt when formulating the Wheeler-DeWitt equation for quantum gravity. The equation describing the quantum state of the universe appears to eliminate time entirely. It treats the universe as a whole without requiring an external clock. This has become known as the problem of time in quantum gravity. How can a timeless equation produce a universe in which clocks tick, stars evolve, galaxies collide, civilizations arise, and history unfold? No universally accepted answer exists.
Carlo Rovelli has argued that time may be relational rather than absolute. Objects change relative to one another, and what we perceive as time emerges from these relationships rather than existing as an independent cosmic backdrop. Others explore thermal time, causal structures, or entirely different mathematical frameworks. Despite decades of research, the question remains open. And that is perhaps the most astonishing fact of all. Every clock ever built, from ancient sundials to atomic clocks, accurate to within a second over billions of years, measures time with extraordinary precision. Yet physics still cannot say with confidence what time fundamentally is. If we do not yet understand time itself, then asking whether there exists a smallest possible event is not merely asking about tiny intervals. It is asking whether change, causality, and the flow of reality emerge from something even deeper than spacetime. That possibility places our question at the very frontier where cosmology, quantum mechanics, gravity, and information theory all converge, and where the next great revolution in physics may already be waiting. Imagine shrinking yourself until an entire galaxy becomes smaller than a grain of dust. Shrink further, the Milky Way disappears, the solar system vanishes. Atoms become larger than stars once seemed. Protons become enormous worlds. Quarks become distant objects separated by what now feels like vast landscapes. Keep going. Eventually, you reach a scale where every experiment humanity has ever performed ends, not because there is a physical wall, not because reality tells you to stop, but because our mathematics simply cannot continue. This is perhaps the most honest boundary in all of science. Physicists often speak confidently about black holes, neutron stars, gravitational waves, exoplanets, and the expansion of the universe, because these ideas are supported by observation. But when we approach the Planck scale, the language changes. Words such as perhaps, may, could, and candidate theory suddenly become common. This is not uncertainty born from carelessness. It is uncertainty born from intellectual honesty. Modern physics openly admits that it does not yet possess a complete theory of nature. That admission itself is extraordinary. Most scientific fields spend their time refining established knowledge. Fundamental physics still spends much of its effort asking whether its most basic assumptions are even correct. Perhaps the greatest clue comes from black holes. For much of the 20th century, black holes were regarded as remarkably simple objects. General relativity predicted that once matter crossed the event horizon, only three measurable quantities remained: mass, electric charge, and angular momentum. John Wheeler summarized this elegantly by saying, "Black holes have no hair." The phrase meant that every complicated detail about the matter forming a black hole seemed to disappear. Whether the black hole formed from collapsing stars, gas clouds, or entire stellar systems appeared irrelevant. Nature erased the details. Then Stephen Hawking made a discovery that transformed this picture forever. Using quantum field theory and curved spacetime, he showed that black holes slowly emit radiation. The result was astonishing, because Hawking radiation is almost perfectly thermal. Thermal radiation carries remarkably little information about its origin. That immediately produced one of the greatest puzzles in theoretical physics. If a black hole completely evaporates through Hawking radiation, what happens to the information describing everything that ever fell inside? Quantum mechanics insists that information cannot simply disappear. The evolution of a quantum system is unitary, meaning the complete information encoded in its wave function is preserved over time. General relativity seemed to suggest otherwise. For decades, this contradiction became known as the black hole information paradox. It may sound like an abstract debate among theorists, but its implications reach astonishingly far. If information can truly disappear, quantum mechanics must be modified. If information cannot disappear, our understanding of space-time, black holes, or both must change. Either possibility implies that our current picture of reality is incomplete. Over the past 20 years, remarkable progress has emerged from an unexpected direction: quantum information theory. Instead of asking what matter is made of, many physicists began asking something even more fundamental: what is information? Claude Shannon had already shown in 1948 that information could be treated mathematically, independent of the physical medium carrying it. Whether encoded in radio signals, DNA, computer memory, or neural activity, information obeys universal principles. John Wheeler later condensed this growing realization into a famous phrase: "it from bit." His suggestion was radical. Perhaps every physical object, every particle, every field, every galaxy, and perhaps space-time itself ultimately emerges from information. At first, this sounded almost philosophical. Today, it has become one of the most active research directions in theoretical physics. Quantum computers provide an intriguing example. Unlike ordinary computers that manipulate bits taking values of either 0 or 1, quantum computers manipulate qubits existing in superpositions of multiple states. These devices are built directly from the strange principles of quantum mechanics. Remarkably, many mathematical techniques developed for quantum computation now appear in research on black holes, space-time geometry, and quantum gravity. Entire branches of modern theoretical physics increasingly resemble information science. The question is no longer merely what is matter. It has become what information defines matter, and perhaps even what information defines space-time. If that shift is correct, then our original question acquires an entirely new interpretation. A smallest possible event may not correspond to the shortest interval of time. Instead, it could represent the smallest possible change in the informational structure of reality. That is an astonishing idea. We usually imagine events as things happening. Perhaps events are actually updates in the informational structure of the universe. If so, then space, time, matter, and energy may all emerge from an even deeper computational or informational framework. Not necessarily a computer simulation, but a universe whose deepest language is information rather than objects. This remains speculative, but it is grounded in serious research rather than science fiction. Another clue comes from entropy. Entropy is frequently misunderstood as simply disorder. In modern physics, entropy measures the number of microscopic configurations compatible with a macroscopic state. Imagine shuffling a deck of cards. From your perspective, the deck simply becomes mixed. From the perspective of statistical mechanics, the number of possible microscopic arrangements increases enormously. The second law of thermodynamics tells us that the total entropy of an isolated system tends to increase. This simple law governs astonishingly diverse phenomena. Ice melts, stars burn nuclear fuel, galaxies evolve, black holes grow. Even the direction we perceive as the flow of time is intimately connected with entropy. The future differs from the past because entropy increases. This idea is known as the thermodynamic arrow of time.